The solar system's planetary family has recently been thrust into the spotlight due to startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku. They have brought Pluto back into focus with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen? And what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets that could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination. Angled at 17 degrees to the ecliptic plane, the path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricate mechanics of space. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms azimuthal libration, latitude libration, and the VZK oscillation are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is azimuthal libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zeipel, Litov, and Kozai, who studied how objects move in space. It explains how three celestial bodies, like Pluto, Neptune, and the Sun, interact gravitationally. This pulling affects their movements, and in Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation shows that even if things in space seem wild and random, certain patterns and rules help maintain order. All of these components contribute to keeping Pluto's orbit stable, ensuring it doesn't crash into Neptune or veer off course. This three-body problem helps us understand how these paths change because of the way these space objects pull on each other. Studying this aids our understanding of Pluto, our solar system, and even distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a special connection with Pluto. For every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one involved. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn contributes as well. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for billions of years. In essence, Neptune, Jupiter, and Saturn are all working together to ensure Pluto moves safely in space without encountering trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Celestial bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies, especially with talks of. Understanding Pluto's orbit is crucial, especially with concerns about it possibly crashing into Neptune in the future. This provides a clearer picture of the solar system's dynamic nature. Pluto's case demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been extremely helpful for scientists in figuring out how Pluto moves through space. These simulations use complex math to mimic how Pluto and other celestial bodies, like Neptune, pull on each other. By adjusting small details in the simulations, astronomers can observe how even minor tweaks can lead to big changes in Pluto's path. Back in the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite the stabilizing effects of azimuthal and latitude libration, its orbit can still be quite wild and unpredictable. Even a tiny difference in Pluto's starting position or velocity can lead to vastly different outcomes over many years. However, despite this chaos, Pluto's orbit remains stable for billions of years. This indicates that Pluto's journey around the Sun has an underlying order, even though it initially seems chaotic. Predicting cosmic events, especially involving chaotic orbits like Pluto's, presents a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. Numerical simulations provide a powerful tool for understanding and anticipating the future paths of celestial bodies, but they also highlight the limitations in our predictive capabilities. These models rely heavily on accurate initial conditions, and even slight errors or oversimplifications can lead to vastly different outcomes, making precise predictions daunting. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, Pluto's case reminds us that our knowledge of the universe remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So, why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite the complex forces that seem to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing astronomy, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the expanding knowledge of our solar system. He views the reclassification not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting the Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The intrigue of these unknowns, according to Tyson, is what makes astronomy so captivating. Furthermore, Tyson understands how space events and discoveries shape public interest in astronomy. He believes that events like Pluto's reclassification or the peculiarities of its orbit are opportunities to engage the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes counterintuitive nature of space mechanics, Tyson helps the public appreciate the wonders and mysteries of the universe. Alongside other scientists, Tyson is at the forefront of warning the public about the potential danger of Pluto's unpredictable course. After studying Pluto for many years, Tyson has raised concerns that the three-body problem could be a real concern when it comes to Pluto, suggesting that a collision with Neptune is long overdue. Moreover, he emphasized how such a collision could completely alter the balance of the universe, potentially triggering catastrophic consequences all the way to Earth. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an immense amount of energy, likely shattering Pluto, given its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially creating hazards for other planets and their moons. For Neptune, such an impact could alter its atmosphere and potentially its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and popularizing science, also offers a unique perspective on this debate. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics provide deep insights into the mysteries of space phenomena, like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a window into the future of space exploration. He believes that understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto can provide crucial insights for future space missions. This knowledge could help navigate the solar system more effectively, predict potential hazards, and even plan missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, offering a blueprint for how we might approach and understand distant worlds. When it comes to planetary physics, Kaku often discusses the deep connections between celestial mechanics and theoretical physics. He believes the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated phenomena. They are connected to the fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to understand these principles at the most fundamental level. He often suggests that by studying the complexities of celestial mechanics, like the orbit of Pluto, we can gain insights into the underlying laws of the universe. Much like Tyson, Kaku announced this impending collision as well, linking it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in astrophysics, offering a unique observational opportunity that could potentially relate to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system could produce extreme conditions of energy and gravity, potentially creating scenarios where effects predicted by string theory might become observable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. Furthermore, the gravitational waves produced by such a collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. These waves could potentially carry signatures or anomalies that align with or challenge the predictions of string theory. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, showcase the intricate and dynamic nature of space. The three-body problem is not the only mystery of the universe we have yet to find answers for. Many other potential catastrophes are predicted to occur. The possibility of planetary collisions in space, while extremely rare, cannot be completely ruled out. The dynamics of planetary orbits can be influenced by various factors, including the gravitational interactions described by the three-body problem. In space, there are systems with many planets close together, like the TRAPPIST, one system, which has 7 planets about the size of Earth. These planets can pull on each other with their gravity, creating a kind of rhythm or pattern in the way the planets move, called orbital resonances. Over time, these rhythms can shake things up and make the planets' paths less stable, potentially leading them to bump into each other. However, even in crowded systems like TRAPPIST-1, collisions aren't happening right now. Scientists watch these systems closely to learn more about how planets can affect each other's paths. Understanding these patterns helps us learn more about how planets move in space, especially when they are very close to each other. Rogue planets, drifting through space without a star, add another unpredictable element. These planets, once part of a star system, get ejected due to gravitational disturbances or other celestial events, such as the close passage of another star or the dynamic instability in multi-planet systems. Over time, these rogue planets drift in space, traveling vast distances and potentially entering regions far from their point of origin. During their lonely journey, rogue planets carry the potential to cross paths with other star systems. If one of these wandering planets crosses into another solar system, there's a small chance it could collide with a planet in that system. However, space is incredibly vast and mostly empty, making the odds of a rogue planet directly hitting another planet very slim. The sheer scale of interstellar distances and the relative rarity of planets in open space act as buffers against frequent collisions. Additionally, rogue planets are not very common compared to the number of stars and planets in stable orbits, making such encounters even more unlikely. In cases where galaxies merge, their respective star systems can be thrown into disarray. The vast interstellar distances make it somewhat improbable for planets to collide directly during these cosmic events. However, the immense gravitational forces at play dramatically alter the orbits of stars and planets within the merging galaxies. This turmoil can lead to planets being violently ejected into the cold, dark expanses of intergalactic space, becoming rogue worlds untethered to any star. Alternatively, these gravitational disruptions could potentially lead to scenarios where planets are ejected from their orbits, collide with each other, or crash into their host stars. In some cases, the gravitational reshuffling can even trigger the formation of new celestial bodies or lead to the ignition of new stars as gas and dust are compressed under extreme conditions. In our own solar system, theories about the late heavy bombardment suggest that a period of increased comet and asteroid collisions occurred due to gravitational disturbances from the outer planets. This phenomenon, believed to have taken place approximately 4 billion years ago, indicates a time when the solar system was a much more chaotic and violent place. The gravitational disturbances are thought to have been caused by the migration of the gas giants, which disrupted the orbits of numerous smaller bodies in the Kuiper Belt and asteroid belt. As these objects were thrown into erratic paths, many found their way into the inner solar system, leading to a spike in impacts on the terrestrial planets, including Earth. While this event did not involve planet-planet collisions, it demonstrates how gravitational interactions can lead to significant changes in the trajectories of celestial bodies. This bombardment likely played a crucial role in shaping the surfaces and geological histories of these planets, including the potential delivery of water and organic materials to Earth. Over the very long term, as stars evolve and lose mass, the orbits of planets can expand and potentially intersect. This process is particularly evident in systems where stars end their life cycles. As a star ages and burns through its nuclear fuel, it undergoes significant changes in mass, especially during stages like the red giant phase or when shedding material in a planetary nebula. These changes in stellar mass can dramatically affect the system's gravitational balance, causing the orbits of surrounding planets to drift outward or become more compact. This is more likely in multi-star systems, where complex gravitational interactions can lead to unstable orbits more easily. In such systems, the gravitational pull from multiple stars can interact unpredictably, worsening orbital shifts and increasing the likelihood of orbital crossings. This can lead to scenarios where planets may be captured by another star in the system, collide with other bodies, or even be ejected into interstellar space. In all these scenarios, the actual occurrence of a planet collision is still considered highly unlikely. The vastness of space and the relative smallness of celestial bodies make direct collisions rare events. However, these possibilities are of great interest to astronomers and astrophysicists, as they provide insights into the dynamics of planetary systems and the evolution of galaxies. The study of Pluto's orbit represents the continuous quest for knowledge and understanding in the field of space exploration. As Tyson and Kaku have shown, every discovery and every piece of new knowledge brings us closer to unraveling the complex nature of our universe. It's a journey that challenges our perceptions, expands our horizons, and inspires future generations of explorers and scientists. This constant observation can help us predict major catastrophic events that might occur in the future, such as the collision of Pluto and Neptune. Thanks for exploring with us. If you enjoyed these revelations, click now on the next video that pops up on your screen. It's unbelievable